Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Fatima Tudaifa, and I'm here with my partner, Iskina Gaitsa. And today we will presenting about computational linguistics. The computational perspective. Computational linguistics seeks to develop the computational machinery needed for an agent to exhibit various forms of linguistic behavior. By agent, mean both human beings and artificial agents such as computer programs. By machinery, mean computers programs as well as the linguistic knowledge that they contain. Computers do not have innate intelligence. Their linguistic abilities come from programs written for them. Therefore, computational linguistics is involved in designing and developing programs to carry out linguistic tasks. These programs are based primarily on methods developed by computer scientists, but they use linguistic knowledge developed by linguists. Thus, computational linguistics integrates ideas from linguistics and computer science. Languages involve complex symbol systems, and computers are very fast mechanical symbols processor. There is a natural relationship between linguistic and computational processing, between the complexity of linguistics patterns and the complexity of computational mathematical models. First, morphological processing. Morphology is the study of the structure of words. The automatic task of a morphology analyzer is to take a word in a language and break it down to its stem form along with any affixes it may have attached to that stem. Note that the morphology analyzer will not be able to identify the syntactic role of words. This is the next task of the syntax parsing program. An important strategy in computational linguistics is to treat language as modular or composed of different subsystems and to develop and integrate modules for the different subsystems. A. Tokenization. Usually, the first step in morphological analysis is to identify the word, a process called tokenization. This can be very simple in a language like English, where words are delimited by spaces and punctuation characters, and where sentences start with a capital letter. In languages where orthography or written form does not mark word boundaries with spaces or punctuation marks, tokenization is more of a challenge. In some of these languages, the idea of what a word means may not be clear. Consider the following Japanese sentences containing Chinese kanji and Japanese hiragana characters. And there's the example. With Chinese kanji characters in particular, there is genuine ambiguity about how certain common multi-character words should be segmented, and different morphological analyzers sometimes differ in their segmentation decision. B is morphological analysis and synthesis. The automatic morphology analyzer takes words and breaks them down into their component morphemes, stems, and affixes. Sometimes, instead of a full morphological analysis, a simple stemming algorithm is used which removes the suffix to arrive at the stem shape. Stemming is used in applications such as search engines, which are very happy to find when given a blunt search word, but are less useful in situations where depth of syntactic and semantic analysis is required. Another strategy is to use a fully inflected lexicon, which ideally includes all possible affixes of every word in the language. The analyzer only looks for words in the list. Such lists are almost certainly not exhaustive, and they can become too large and unwieldy for the computer to handle. A typical strategy for applying morphological rules is the pattern action approach. The computer programs identifies words that match the pattern of the rules, then knows the morphological component of the word as determined by the rule. Number 2, syntactic processing. In this section, we will introduce the problem of how to get a computer to characterize the grammatical structure of sentence. Given a set of linguistic rules that describe how sentence elements can be put together, or grammar, a computer program called a syntactic parser will try to find the best grammatical analysis of a sentence. If the sentence is ambiguous, that is, if it has more than one possible grammatical structure, the syntax parser will perform all analysis. A is context-free grammars. The toy grammar recognizes four different kinds of VP: aux V, V, NP, V, and aux V, NP, and three kinds of NPs, G and N, and pronoun. The categories, the left of the arrow in the left-hand column, are structural categories. They can be expanded into other categories, but not directly into words. The categories to the left of the arrow in the right-hand column are lexical categories, or parts of speech. They map to particular words. All the categories to the left of the arrow are called non-terminals, since they rewrite to other categories of or words. Words, in turn, don't rewrite to anything and are therefore called terminals. This toy grammar includes only three different verbs: one auxiliary verb, one determiner, two nouns, and one pronoun. But even so, it can describe quite a variety of sentences. Grammar written in this format is called context-free grammar. B. Parsing. One way to represent the hierarchical syntactic structure of a sentence is called a parse tree. Here are two parse trees. The parser takes "I can fish" as input, the processes it using the grammar to produce parse trees. And the picture in number 6 and number 7 as output. And C, part of speech tagging. Instead of having a parser considering all part of speech of ambiguous words, it is possible to reduce ambiguity before parsing by running a program called a part of speech tagger before parsing. For each word that has more than one part of speech, the marker gives the most probable part of speech. This is done in the context of rule handed down by human intuition, as well as rules derived by machines that learn from a collection of example sentences tagged with part of speech. While part of speech tagging can reduce ambiguity because it cannot reduce other types of syntactic ambiguity. And next, D, beyond context-free grammars. One problem with context-free grammar is that they require a lot of rules. For example, if we want to add subject-verb agreement to grammar so that we get a successful parse for I dance and he dances, but not he dance or I dances, we have to create two as a rule. One that combines third-person singular NP with third-person singular VP, and one that combines non-third-person singular NP with non-third-person singular VP. In addition, we must create separate rewrite rules for each of these more specific NP and VP categories. And as we add new SS type to cover requires queries and imperatives, we have to create the appropriate branch agreements in them as well. This approach and produce descriptively adequate grammar, but it is not very elegant or efficient. E. Statistical parsing. Linguists need to decide on the rule of phrase structure, a collection of non-terminal structural categories and terminal lexical categories to be included in the grammar. The linguist then takes a collection of text called a corpus, ideally representative of the language sample, and analyze and marks the sentence in those texts with a parse tree. Once a large corpus has been described in this way, creating a tree bank, computer can be taught to induce grammar from it. How can a computer learn grammar from a tree bank? First, the program counts how often each type of syntax configuration is found in the annotated tree bank. Each configuration is represented as a rule like the one in orthogrammar, and each rule is weighted according to how often it appears in the tree bank. The probability of the parse tree can be viewed as the probability of all the rules in that the parse tree occur together, assuming that the probability of a rule in the parse tree is independent. The presence of another rule in the parse tree. The probability of the parse tree is calculated as the product of the probabilities of all rules in parsing the tree. Number 3 is semantic processing. A, word meaning. For a syntactically unambiguous sentence consisting of words that each have only one meaning, this will be relatively simple. Each word at the bottom of the tree will be visible in the lexical database, essentially a digital dictionary, and the meanings of the words will be linked together according to the structural relations represented in the parse tree to generate the meaning of the sentence. B. Sentence meaning. The general assumption underlying the computational approach to semantics is that the meaning of the whole is systematically composed of the meanings of the parts. And a computer program based on semantic composition unifies the meaning of a sentence from the meaning of the words and phrases that compose it. The computational semantics is mostly concerned with representing this type of semantic function. The rules for assembling semantics of the larger than smaller phrase. Natural language generation. There are two main steps in natural language generation. Deciding what to say called strategic generation and deciding how to say it called tactical generation. In strategic generation, the system must select specific content from the dataset and decide on the overall structure of the output, which can be as short as a phrase or as long as an entire document. Strategic generators determine which message units to include in text and plan the structure or discourse model of the output text. In tactical generation, the system generates sentences from abstract message units defined by the discourse model. In the simplest case, each message unit can be expressed in one sentence, but several messages can be combined in one sentence, or one message can be spread in several sentences. The tactical generator applies information from the discourse model to make this kind of sentence building decision. To construct sentences, tactical generators use a semantic representation of the intent, output, and grammar. Usually, there will be many possible sentences that can be built from semantic input because generation involves making various syntactic and lexical choices. It helps to set the grammatical rules in terms of these choices. And the next material will be explained by Iskina.
Thank you, Fatima. And here there is probabilistic theories. Given the success of statistical methods, we have at least two ways to construct linguistic theory, namely the traditional way of arriving the rules by hand based on linguistic intuition and totally outdated. How to derive rules automatically based on statistical generations from curves. Statistical analysis was initially discredited by most linguists. They argue that statistical methods are based on inductions from an infinitely small sample of languages. So they will misinterpret the language. These linguists also claim that the actual utterance produced by the speaker are an insignificant disturbance and is not systematically related to the speaker's linguistic competence because the language corpora model is only performance and also statistical analysis of the corpora cannot represent linguistic competence. But many linguists do not find the competence competency performance differences to be obvious. Next. Fatima, next. In particular, sociolinguists argue that the variability of linguist performance is systematic, predictable, and meaningful to language speakers. However, the inside guide from the large corpus may apply to languages outside the corpus. If statistical rules induced from examples work as well as rules derived from intuition, then this shows that probabilistic statistical linguist rules can help explain or model human linguist behavior. It also shows that humans can learn variant rules of induction using statistical regularities. Next. Fatima, next. Rel- bentar. Related technologies. The impact on the related technologies. The impact of computational linguists on society depends on the application. It allows computers over the years have used more and more computational linguist tools in applications such as multilingual word processing, spelling correction, and grammar checking. And the last decade, dramatic increases in computer speed and the ability to cheaply store a large amount of information online have resulted in the amount of information available to computers, with much of it in natural language. Certainly, other technologies provide opportunities to embed and apply computational linguistics into everyday life. First, extraction of information, which is now a commercially hot technology. Attempts to derive information from text It's Information extraction programs automatically populate templates or tables from natural language input. For example, for a terrorist event, the template slot that must be filed in may include the perpetrator, the victim, the type of offense, as well as the place of and time of its occurrence. What is extracted here is not the meaning of individual sentences, but information about certain entities referred to in the text such as events, people, organizations, location, and time. These are called name entities and the spatial relationship between them. The summary. Information is gathered together to represent the content of the document. Information extraction programs can extract relevant content from hundreds of documents in the time it takes a human to read and extract the content. Next. And the second, speech recognition. Voice recognition is a commodity available and found embedded in many everyday applications, including telephone access to business services, speech transcription for digital dictation, automated multimedia information access such as searching for radio and TV news broadcasts, and various other uses. Speech recognition uses a dictionary that lists the pronunciation of words in its vocabulary expressed as a sequence of phonemes. Speech recognition uses several sources of knowledge, namely an acoustic model for predicting the probability of a particular input sound wave matching a particular sequence of phonetic segments. The pronunciation model uses the result of the acoustic model to predict the probability of a particular telephone sequence matching a particular word. The language model then predicts the probability of each word sequence identified by the differentiation model. The rules in the two models have probabilities and estimated from the training data. Next. And the third is speech synthesis. Speech synthesis system usually take written text as input and generate speech. The information program marks the text and processes it first to detect the right names, numbers, present tense, and Next step is to convert this written representation into an actual sound sequence by means of which the acoustic information from the pronunciation model is processed, together with a mathematical procedure that calculates the pitch, amplitude, and timing of the sound waveforms expressing the sequence of phonetic elements. In a sentence like I can fish, any of the three words can be stressed depending on the focus of the speech. This information and much other information related to prosody is not available for synthesizer. Next. In a text-to-speech system, the computers does not know what it is talking about. After some prosodic information is added, for example, standard patterns such as raising intonation for questions, the information in the text-to-speech system is fed with the signal processing module that produce the final audio output. Currently, this model is mostly based on concatenative synthesis, in which pre-recorded speech with voice files are combined into one. Speech synthesis is invaluable in many applications, including telephone access to business services, assistance for the disabled, blind, as well as those with speech difficulties. education, toys, navigation system, and weather and emergency bulletins. And fourth, machine translations. Machine translation, or MT, field machine translation, is the oldest application field of computational linguistics, dating back to the early years of the Cold War. One of the first demonstrations of a working region British MD system was carried out in 1954 by the combined Georgetown IBM system Dossard 1955, in contrast to the translation of literary text, where a great deal of creativity is MD focuses on translation that preserves the information content of the search language as much as possible while translating it in a natural form is the search language of the target language. Next. Its main advantage is that it is economical, especially when the volume of text is such that it is impossible for humans to translate it. Lower accuracy translations may be sufficient to get the gift of some language search, such as news headline search engine result or email messages. Whereas for higher quality result, human force machine translation editing is often required. MT poses challenges for many areas of computational linguistics as it involves understanding speech in one language and generation of speech in another. LMC system tend to translate sentence by sentence, and with a few exceptions, do so while ignoring the context of this discourse. Usually personal names, number, abbreviations, as accidentally translated Next. Following are three general approaches to MD. First, the direct approach looks up words from the search patterns in a bilingual dictionary. Select the most appropriate words translation by several methods, and then rearranges the selected words translation based on the target language word order. The string of words then undergoes morphological synthesis, adding the necessary affixes. Translating between very similar languages. And the second, the transfer approach, the most widely used. Contrast, contracts and intermediate syntactic or semantic representation of tools that map structure across languages based on contrastive analysis of two languages and a target language generation component. Next. And the third, in the interlingual approach, one system represents one concept for each word in each language, or the system breaks down meaning into primitives which are considered universal. For example, Japanese has at least three words for rice: gohan for cooked rice default, kome for raw rice, and raisu for frying rice. The English-Japanese committee system was distinguished four types of rice concept corresponding of to three Japanese words and one English word, or it can choose to ignore the differences and map them all into one primitive concept of rice, or even one primitive concept of grain. Key challenges in computational linguistics, where computers algorithms are very well understood getting computers to acquire some of the linguistic and
Silakan yang mau bertanya. Ya, Teteh, mau nanya apa?
Wait a minute. Can you briefly explain what tokenization is? Thank you.
Parisa mau nanya apa?
In the PowerPoint mention a word of tree bank. What is the meaning of tree bank?
Thank you. Silakan, ada yang mau bertanya lagi?
Boleh nanya?
Enggak.
Okay, so there is a question that why is there a probabilistic theory in linguistics? Thank you.
Thank you, Hani and Parisa. And please wait for the answer. I want to answer the February question. Can you briefly explain what tokenization is? The tokenization is the process of dividing text which can be in the form of sentences, paragraph, or document into certain tokens or parts. For example, tokenization of the sentence, I just ate spicy meatballs generated 6 tokens, namely, I just ate spicy meatballs. Jadi tokenisasi itu kayak seperti proses untuk membagi teks yang dapat berupa kalimat, paragraf atau dokumen menjadi token-token atau bagian-bagian tertentu. Contohnya seperti I just ate spicy meatballs, aku baru saja makan bakso pedas. Hasilnya 6 token, yaitu aku baru saja makan bakso pedas. Cukup. Apa kedengaran suara saya?
Kedengaran Bulan, terima kasih.
Selanjutnya, I will answer Farisha Jasmine question. Tree bank, what is the meaning of tree bank? In linguistics, izin menjawab pertanyaan Farisa. Apa itu tree bank? Jadi tree bank itu korpus teks yang diuraikan yang menjelaskan struktur kalimat, sintaksis, atau semantik. Konstruksi korpora yang diurai pada awal 90-an merevolusi linguistik komputasi yang dibentukkan dari data empiris skala besar. Is that enough, Farisa?
Thank you.
Thank you.
Izin menjawab pertanyaan dari Hanif. Why is there a probabilistic theory in linguistics? Because over the that language is the categorical and that linguistic component is discrete. However, it is becoming increasingly clear that many levels of representation, from phonemes to sentence structure, exhibit probabilistic traits, as do language faculties. The conceptualizes the categories as distributions and view language knowledge not as a set of minimal categorical boundaries, but as a set of gradient rules that can be characterized by statistical distributions. Is that clear?
That's clear, Iskina. Thank you.
Sudah tidak ada yang ingin ditanyakan lagi. Saya tutup presentasinya. Mohon maaf apabila masih banyak kesalahan. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Iskina dan Fatimatul. Terima kasih semua. Saya N ya.